So the first example is we need to find the area bounded by the curve y is equal to 9 minus x squared and the x-axis. Of course, y is equal to 9 minus x squared is a parabola opening downward, and the area must be bounded below by the x-axis. So we will have area under the curve y is equal to 9 minus x squared. So let us consider the curve y is equal to 9 minus x squared. Okay, of course, we know that this is a parabola, but let us write it first in the standard form to give us the intersection with the x-axis, and to let us have this in the standard form to give us the vertex, and then later we will get the intersection with the x-axis. So if we have y is equal to 9 minus x squared, we can also write this as x squared is equal to negative y plus 9. Now, writing it in the standard form, we need to factor out whatever is the numerical coefficient of y. So the numerical coefficient is negative 1. So we factor out negative 1. So just express this as negative quantity y minus 9. So the standard form of the parabola is x squared is equal to negative quantity y minus 9. It is a parabola opening downward, and the vertex of the parabola is at 0, 9. Okay, we need to determine also the intersection of the parabola with the x-axis. So we need to get the x-intercept. And of course, to get the x-intercept, we need to set y is equal to 0. So considering the equation or the curve y is equal to 9 minus x squared, when y is equal to 0, then 0 is equal to 9 minus x squared. And we can also write this as x squared is equal to 9. Getting the square root of both sides of the equation gives us x is equal to plus or minus 3. Okay, therefore, there are 2 points where the curve will intersect the x-axis. Okay, these are at negative 3, 0, okay, and positive 3, 0. These are the x-intercept. Okay, let us draw the parabola here. Okay, let this be the y-axis, and let the horizontal axis be the x-axis. Okay, and the vertex of the parabola is at 0, 9. So the vertex is on the y-axis. 4, 5, 6, 7, 8, 9. Okay, this is the vertex of the parabola at 0, 9. And of course, the parabola will intersect the x-axis at negative 3, and x equals negative 3, and x equals positive 3. Let me have a different scale on the x-axis to emphasize. Okay, and this point is negative 3, 0. Okay, we have x is equal to negative 3, and x is equal to positive 3. Hence, if we will draw the parabola with vertex at 0, 9, opening downward, intersecting the x-axis at x is equal to negative 3, and x is equal to positive 3. Okay. So we are actually considering this region. We need to get the area of this region. Now, we have to take note also that there is symmetry with respect to the y-axis, right? Basically, y is equal to 9 minus x squared is an even function. So there is symmetry with respect to the y-axis. And since there is symmetry with respect to the y-axis, okay, the area to the right of the y-axis on the first quadrant is equal to the area of the region on the second quadrant. Okay, so we might as well get the area of the region on the first quadrant and simply multiply it by 2. But before we do that, the next thing to do is to draw the representative element. I told you earlier that the representative element is the representation of the infinitely many rectangles in the region. And we will just need to emphasize the element. And if we will use the vertical element, of course, it is parallel to the y-axis. The element must touch the boundaries, okay, above. Okay, it is bounded by the parabola. So we can call this point as x, y, okay, any point on the parabola. And the parabola, of course, is y is equal to 9 minus x squared. Okay, so this is the representative element. And of course, since the representative element is a rectangle, the area of the rectangle is equal to the length times the thickness or the base. Now, considering this point, okay, whose coordinates are x and y, the element touches the parabola. So the distance of the point xy from the x-axis is y. So that is the length of the element. And the thickness, of course, is delta x. And by definition, delta x is equal to the differential of x. So after drawing the element, we can now get the area of the element. Of course, the area of the element is equal to the length y times the thickness dx. And if we will evaluate this within the limits or within the region, or within a closed interval from -3 to +3, then that will give us the area of the region bounded by the parabola y is equal to 9 minus x squared and the x-axis. But as I told you earlier, we can just consider the area on the first quadrant, okay, which is exactly equal to the area on the second quadrant. So the area of the region is also equal to the integral of y dx. Okay, y dx is the area of the element. Okay, and considering the area on the first quadrant, now the origin is at 0, 0, 0. So the lower limit will be 0 and the upper limit is 3, and we will just multiply it by 2. The integral of y dx from 0 to 3 is the area of the region on the first quadrant. Just multiply it by 2 to consider the area on the second quadrant. Okay, so the area of the whole region, which is the integral of y dx from -3 to 3, is also equal to the integral of y dx from 0 to 3 times 2, since there is symmetry with respect to the y-axis. Okay, but of course we cannot proceed yet to integration, since the variable of integration is x and the integrand is still in terms of y. Therefore, we have to express the integrand in terms of the variable of integration x. And y is equal to 9 minus x squared. Therefore, the area is equal to 2 times the integral from 0 to 3. Okay, y is 9 minus x squared times the differential of x. And evaluating the integral gives us integral of 9 dx is 9x minus the integral of x squared dx is x cubed over 3. And we are going to evaluate this from the lower limit 0 to the upper limit 3. Okay, so we have 2 times. Now evaluating the definite integral at the upper limit x is equal to 3, then we can replace x by the upper limit 3. So we have 9 times 3 minus 3 raised to the third power over 3, okay, then minus the value of the integral at the lower limit 0. And of course, when x is equal to 0, everything is 0. 9 times 0 minus 0 raised to the third power over 3. Okay, so that gives us 0. And simplifying gives us 2 times. 9 times 3 is 27 minus 3 raised to the third power is 27, and dividing it by 3 will give us 27 over 3 is 9. Okay, hence we have 2 times 18, and 2 times 18 is 36. Therefore, the area of the region, okay, bounded by the curve y is equal to 9 minus x squared, and the x-axis from x equals -3 to x is equal to 3 is 36 square units. Okay, now we can also solve this problem by using the horizontal element. Okay, but of course, not all problems can be solved in two ways, meaning both the vertical element and the horizontal element. There are times that it is more convenient to use the vertical element. There are times that it is more convenient to use the horizontal element. Now, in this case, we can use any, okay, either the vertical element or horizontal element. So to show how to do it using the horizontal element, okay, we will consider the same problem, the same region, the area, the region bounded by y is equal to 9 minus x squared and the x-axis. Okay, and let us consider solving it in this other page. No? So we will consider again y is equal to 9 minus x squared. And of course, it is a parabola opening downward with vertex at 0, 9. Okay, let us draw again the figure, the illustration. Okay, from the previous discussion, the vertex of the parabola is at 0, 9, and it intersects the x-axis at x equals -3 and x is equal to +3. Okay, therefore, we will consider again this region, the region bounded by the parabola y is equal to 9 minus x squared. Okay, so we are considering again this region. Okay, of course, this is y is equal to 9 minus x squared, and we have below the x-axis. And just like what we did in the first solution, let us consider the area on the first quadrant and then just multiply it by 2. So the shaded region, shaded by yellow lines. Okay, but this time instead of considering the vertical element, no, we will consider the horizontal rectangular element. Now, this time the element is parallel to the x-axis, and please take note that the element must touch the boundaries, no, the y-axis and the parabola. Of course, this point that touches the parabola is the point xy. And if we will get the length of the element, which is the distance of the point on the parabola, okay, xy, the length is x, and the thickness this time is delta y, and delta y, of course, is the differential of y. And if we will get the area of the area of the element is equal to the length x times the thickness dy. And if we will evaluate this, okay, within the limits of integration, now please take note that the variable of integration is y. So y will go from y is equal to 0 to y is equal to 9. So limit will go from 0 to 9. But we need to multiply this by 2. Okay, why do we need to multiply it by 2? Since we are just considering the region on the first quadrant, the area on the first quadrant. And since you are considering the whole region bounded by the parabola y is equal to 9 minus x squared, and the x-axis, okay, that is from x equals -3 to x is equal to 3, then we will just multiply the area, the integral of x dy from 0 to 9, okay, multiply it by 2. Now, actually, if we are going to extend the line, I mean the element, the horizontal element, not to the uh, second quadrant, to the area on the second quadrant, then the total length will be equal to 2x. So that will give us the same. No? So area is equal to 2 times the integral of x dy from the lower limit y is equal to 0 to y is equal to 9. Okay, hence, this will give us 2 times the integral from 0 to 9. Now, the variable of integration is y and the integrand is x. Therefore, we have to express the integrand x in terms of y. And if we have y is equal to 9 minus x squared, if we will solve for x in terms of y, then that gives us x squared is equal to 9 minus y. And getting the square root of both sides of the equation will give us x equals plus or minus square root of 9 minus y. But since you are considering only the uh, element, okay, on the first quadrant, then we will take the positive root, the positive square root of 9 minus square root of 9 minus y. Hence, we have the area is equal to 2 times the integral from 0 to 9 of x is the square root of 9 minus y times the differential of y. And we can evaluate the integral by power formula of integration. But we need to express the radical in terms of or in exponential form. So square root of 9 minus y is 9 minus y raised to 1/2 times the differential of 1. And using power formula of integration, then we let u is equal to 9 minus y, and getting the differential of both sides, the differential of u is du. The differential of 9 minus 9 minus y is negative times the differential of y. So if we will solve for the differential of y, the differential of y is negative du. So there must be what? A correction factor, which is -1. So evaluating, then we have negative, this is the correction factor, 2 times the integral of 9 minus y raised to 1/2 dy by power formula is quantity 9 minus y raised to 3 over 2 over 3 over 2. And we will evaluate this from 0 to 9. Okay, now before evaluating the indefinite integral within the limits of integration, we can also bring out the reciprocal of 3 over 2, okay, to make the computation easier. Okay, so minus 2 times the reciprocal of 3 over 2 is 2/3. Okay, then we evaluate 9 minus y raised to 3 over 2 at the upper limit 9. So that gives us quantity 9 minus 9. We replace y by 9 raised to 3 over 2 minus quantity, when y is equal to the lower limit 0, then we have 9 minus 0 raised to 3 over 2. Okay, and simplifying will give us negative 4 thirds, okay, times, of course, 9 minus 9 is 0, okay, minus 9 minus 0, of course, is 9, okay, square root of 9 is 3, and 3 raised to the third power is 27, okay, which will give us negative 4 thirds times negative 27, and we can do cancellation. 27 is divisible by 3, so this gives us 9, and negative 4 times negative 9 will give us the area is equal to 36 square units. Of course, it will give us the same value. Okay, when we considered the vertical element, the area is 36 square units. And of course, if we, when we consider the horizontal element, it must give us also the area of the region under y is equal to 9 minus x squared, okay, bounded below by the x-axis, okay, is also 36 square units. But of course, it is more convenient, no, using the vertical element here, okay, in this specific problem, since in the equation we have y is equal to 9 minus x squared, so we don't need to solve for y, okay. The given equation is y in terms of x, okay. So this time we are going to, by the way, if we will evaluate the integral of 9 minus x squared dx from negative 3 to positive 3, it will still give us 36. So you might as well try it. No? Okay, so this time we will consider the second example. And we have the curve y squared plus x minus y is equal to 5. So we will find the area bounded by the curve y squared plus x minus 4y is equal to 5 and the y-axis. Okay, so this time we have the second degree term y, therefore the parabola opens to the left, and the region will be bounded on the left by the y-axis. So let us consider first the equation or the curve y squared plus x minus 4y is equal to 5. Okay, so to draw to draw the region, it will be more convenient for us to express first the given equation in standard form. So we need to transpose x to the other side of the equation. Okay, giving us y squared minus 4y is equal to negative x plus 5. Of course, we need to complete the square of y squared minus 4y, and to do that, we can add 4. 4 actually is the square of the coefficient of one half of the coefficient of y. Negative 4 raised to this negative 4 over 2 is negative 2, and negative 2 raised to the second power is 4. So we have to add 4. Okay. So 1/2 of negative 4 is negative 2. Square of negative 2 is 4. And since we added 4 on the left side, we need to add 4 also on the right side. Now, the left side is now a perfect square trinomial whose factors are 1, y minus 2 raised to the second power. And we can simplify the right number, negative x plus 9. And if we will write this in the standard form, then we have the standard form of the equation of the parabola, y minus 2 y minus 2 raised to the second power is equal to factor out -1. So the other factor is x minus 9. So the standard form is y minus 2 raised to the second power is equal to negative quantity x minus 9. And this is an equation of the parabola opening to the left with vertex at 9, 2. Okay, and since we will find the area of the region bounded by the parabola and the y-axis, we also need to get the intersection of the parabola with the y-axis. So we will get the y-intercept. And of course, to get the y-intercept, we have to set x is equal to 0. And considering the equation y squared plus x minus 4y is equal to 5, when x is equal to 0, then y squared minus 4y is equal to 5. Transposing 5 to the left member gives us y squared minus 4y minus 5 is equal to 0. Of course, the left member is factorable. Factors are y minus 5 and y plus 1 equated to 0. And if we will equate each linear factor to 0, it will give us y minus 5 equals 0, y is equal to 5, and y plus 1 is equal to 0, y is equal to -1. So the curve will, or the parabola, will intersect the y-axis at y is equal to -1 and y is equal to 5. Okay, so let us draw the region. Okay, let this be the y-axis and let this be the x-axis. Let us locate the vertex. The vertex is at 9, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 1, 2. Okay, I use different scale on the y-axis. Okay, this is the vertex of the parabola at 9, 2. And the parabola will intersect the y-axis at y is equal to -5 and y is positive 5 rather, and y is equal to -1. This is 5, 0, 5, and then 0, -1. And if we are going to draw the parabola opening to the left, okay, intersecting the y-axis at -1 and +5, then we are considering this region. Okay, we have the parabola y squared plus x minus 4y is equal to 5, then the y-axis. Therefore, this is the region that we are interested in. We need to find the area of the region. Now, the second thing to do is to draw the representative element. Of course, we have to think, shall we use the vertical element or shall we use the horizontal element? Now, in this case, the horizontal element is more convenient to use rather than using the vertical element. It will be more convenient for us to express y in terms of to express x rather in terms of y rather than doing it the other way around. Okay, so we can use the horizontal element, okay, since it will be more convenient for us to express x in terms of y. So we draw the horizontal element anywhere on the region, and take note that the element must touch the boundaries, the parabola, okay, on the right, okay, and this point is x, y, and of course it must touch the y-axis. And if this is the representative element, then the thickness is delta y, or the differential of y. And the length of the element is equal to x. The distance of the point xy from the y-axis is x. Hence, if we will find, or if we will get the area of the element, of course, is equal to the length times the thickness dy. So we have x times the differential of y. And if we will evaluate this within the limits of integration, okay, from where the variable of integration is y, so we will consider from y is equal to -1 to y is equal to 5. Hence, the lower limit of integration is -1 and the upper limit of integration is 5. Now, to find the area, we evaluate the integral of x dy, okay, from -1 to 5. Variable of integration is y, but the integrand is x, therefore we have to express x in terms of y. And I told you that it will be more convenient to express x in terms of y. So in the equation, y squared plus x minus 4y is equal to 5, we solve for x so that x is equal to 5 plus 4y minus y squared. So going back, then this is equal to the integral from -1 to +5 of, okay, x is 5 plus 4y minus y squared, okay, dy. We will integrate with respect to y. And evaluating the integral gives us, okay, integral of 5 dy is 5y, plus the integral of 4y is 4y squared over 2. Of course, 4 over 2 will give us 2. So 2y squared minus the integral of y squared dy is y cubed over 3. And we have to evaluate this from the lower limit, y is equal to -1, to the upper limit, y is equal to 5. Okay, hence the area is equal to, okay, evaluating the indefinite integral at the upper limit, y is equal to 5 will give us 5 times 5 plus 2 times 5 raised to the second power, okay, minus 5 raised to the third power over 3, okay, then minus the value of the integral at the lower limit, -1. So 5 times -1 plus 2 times -1 raised to the second power minus -1 raised to the third power over 3. And let us try to simplify. Okay, 5 times 5 is 25. Okay, 5 raised to the second power is 25. 25 times 2 is 50 minus 5 raised to the third power is 125 over 3. Okay, then minus 5 times -1 is -5. -1 square is positive times 2. Okay, positive 1 times 2 is 2. Then minus 1 raised to the third power is -1. Negative negative is positive, so this will give us a positive, positive 1/3. Okay, and simplifying further gives us uh, 25 plus 50 is 75 minus 125 over 3. Okay, -5 plus 2 is -3. Negative negative is positive 3. Okay, then minus 1/3. And 75 plus 3 is 78 minus 125 over 3, -125 rather, -125 over 3 plus -1/3 will give us -126 over 3. Okay, so what will it give us? Okay, 78 minus 126 over 3 is 42, right? 42. And 78 minus 42 is 36. Therefore, the area is equal to 36 square units. Okay, so this is how to get the area under the curve. In the first example, we consider a curve, which is a parabola opening downward, and below it is bounded by the x-axis. On the second example, okay, here we consider a parabola opening to the left, okay? So the region is bounded by the parabola opening to the left and the y-axis. Okay, so this is how to get the area under the curve. Now the next part will focus on finding the area between curves.